Alright, so homogeneous linear equations, the general solutions. Okay, so in this section and going forward, we connect different types of mathematical fields together, especially if you're taking linear algebra or going to take linear algebra in the future. So first of all, we started with talking with solving for a differential equation of this aspect. We're going to break it up into two different parts. The first part is the special case is when this is actually equal to 0. Okay, so this is a very special equation. And its definition is called a homogeneous linear equation, and it's going to be really popular going forward. Okay. Again, very special because it's fixed to be 0 and 1 in that aspect. Okay. So any equation of this format is called a homogeneous linear equation. Okay. So a little bit of backtracking. If you guys have taken linear algebra before, if you've had an experience of taking linear algebra, you kind of understand what it represents to be homogeneous. So really, what's really happening based off this order is the second derivative is a linear combination of the other two. Again, if you've taken linear algebra, you understand what that represents. But if you don't, you'll eventually know what that really means. So linear combination means they're linear independent. And we'll talk about that as well in this section as going aspect. But what I mean by that is if I bring this all over, the second derivative is a combination of the first two lower cases. Like that. And if I divide by a, we get the general one you'll be seeing going forward. We'll just so this is a nice one because this represents linear independency in linear algebra. Okay. Now, because we know this aspect, and the key thing is knowing these are linear combinations and linear independent of each other, which we'll define in a little bit, we have a nice form. We know that every solution is of this form. Okay. So if that's the solution of these forms, well, we can backtrack and see, okay, is there a way to find a general equation of this type of form, or can we find an R value that always makes this work? So we're just going to do a little experiment. So because we know this is a solution, let's take the derivatives and just plug it in. And then we plug it into our general homogeneous equation. So it's just going to be a times r squared e to the rt plus br e to the rt plus ce rt all equals 0. So now if I just factor out e to the rt, I get a nice quadratic equation. Now, the nice thing is this is never negative, or actually never 0, because it's an exponential. So what makes this true is this. So that is what I'm actually setting equal to 0. So really, this has a solution whenever I get an R value that makes this actually true. Okay? That is the whole point. And this is kind of nice because this is a simple quadratic. We know how to solve for quadratics. You could factor, which is the biggest one, or complete the square, or everybody's favorite quadratic formula. But now the whole point is finding this R value. Then now we could just plug it back to our original equation, and it actually works out. Okay? Now, because this is so nicely done, and it's done in, or it's a general equation, this is called the characteristic equation. Again, another component of linear algebra. Okay? So this equation is called the characteristic equation of the homogeneous equation, And all we have to do is solve for r gives the general solutions of the form e to the rt. Now again, going backtrack to a little bit of linear algebra. Okay. Because we have a homogeneous equation, we have two options. We either have infinite many solutions or we have no solutions. Okay. Which kind of makes sense, right? Because we have no solution, I mean there's no possibility. But if we have actual solution, there we have a c value. So in general, our equations are going to look like this. Where again, C1 and C2 are arbitrary constants, hence the infinite many solution part. So this is our general solution for a homogeneous equation, okay, where this y1 and y2 represent the r's themselves. Okay. So the next couple of theorems and lemmas correspond to exactly what that is, just going in basic format. So given any initial value problem, we could basically solve for it using our homogeneous situation. Okay. Next one corresponds to linear independency. A pair of functions y1 of t and y2 of t are linear independent on the interval I if they only if either of them is a constant multiple of each other, which makes sense, right? That's what linear independency represents. If there is a constant multiple equals each to the other, then they're linear dependency. Okay. So that's where it comes down to the Worskin, and we'll talk about that a little bit later on as well. So we have a theorem here, just correlating what I summarized before. If y1 of t and y2 of t are solutions to the homogeneous equation and are linear independent on the open interval, then there are unique constants, c1 and c2, such that we have this happening, and it does satisfy the initial value problem, meaning we can find them normally. Okay. Now this is a fun little one. We'll be seeing this much more later on in different portions because linear dependency. So for any real numbers a, b, and c given this format, then there are two solutions in the homogeneous equation that hold if, this is the key thing, y1 or y2 are linear dependent on each other, or in other words, the Worskin is 0. And we'll talk about the Worskin later on in the course as well. Just a little subtle hint what that represents for those linear algebra people itself. Okay. All right, so now we get the final big one we will care about is a general solutions. So we already talked about this one, but how do we actually do them? Because we know y equals e to the rt is our general solution. So each r1 represents its own unique one. This will represent y1, and this will represent y2. Okay? Where r1 and r2 are the factors of our characteristic equation. However, if we have repeated roots, or repeated real numbers, all it's going to be the same thing except this t value in the front of that. So for example, if we have r equaling 2 and 2, this will be the general one just itself. This will be the same, but with a t in front of it. That's the only difference. So which is kind of nice. So whenever you have homogeneous equations, or anything that's set equal to 0 when you want to solve for the differential equation, the key thing is find its characteristic equation, solve for the r value, and that's exactly, we're done. Okay. So everything goes always back to factoring. So let's try this example out. So find the general solution or slash solve the initial value problem for the following. We'll keep going. All right, so first up, this is always going to be r squared plus 5r minus 6 equals 0 to be our characteristic equation. So this nicely factors into a x method, AC method, whatever you are comfortable doing, or guess and check method, doesn't matter to me. Looks like that works. So we get r plus 6 and r minus 1 equals 0. So we get r equal negative 6 and r equals positive 1 as are my answers. Okay. So therefore, our general equation, or general solution, is going to be c1 e to the negative 6t plus c2 e to the 1t, or just that. And that's it. Kind of nice, right? A little easier than the stuff we're doing so far. So let's keep going. All right, now we're solving the initial value problem. So r squared plus 2r minus 1 equals 0. So this time factoring doesn't work. Right, there's nothing that can multiply to give you negative 1 and then add to give you 2. So even this doesn't work, right? Okay, so you have to use the quadratic formula. So after you use the quadratic formula, we get answers in this form. So we get R1 to be, I'll just use that as the positive, and R2 to be the negative. Or I'll just switch them around, just for funsies. Okay, so now our general equations be C1 e to the all of this times t plus C2 e to the all of that times t. There we go. So now we got to solve our initial conditions. So plugging in 0 in for t and setting the whole thing equal to 0. So e to the 0 power is just 1. And same process here. So C1 and C2 are just opposite signs of each other, same number of opposite signs. All right, so we also have to do the derivative. So taking this derivative individually, gives me that. And again, we plug in our conditions. So again, I'm plugging in 0 from t. So really everything goes away except for the first part. And this whole thing equals negative 1 now. All right, so at this point, I'll just bring this over. So minus C1 equals C2. So everywhere I see C2, I'll put in negative 1. So if I just change that to negative C1 and just rewrite some stuff. This becomes positive, and this becomes negative. So these cancel. Put those together. And pretty much dividing everything over, we get C1 is equal to positive 1 over 2 radical 2. Or if you don't like the radicals, you can keep it like this, but if you like the other way, that. Which way, it doesn't matter. All right, so that's C1. So C2 is just the negative of it. So we get our answer, or our solution to this. So C1 was that. Oops, inside. And then minus it. And there we go. So let's keep going. Okay, so again, initial condition, and we want to do one extra step. We want to verify y2 is a solution as well. Okay. All right, so we get r squared plus 4r plus 4 equals 0. Looks like 2 and 2 work. So we get a repeated root. So repeated. So according to our equation, if it's repeated, we're going to just add a t in the front of it. So c1 e to the negative 2t plus c2 was just a t in front, and same thing. All right. So now we just solve for our conditions. So we can start here. Plug in 0 for t's, and we get 1. So that's nice. This all goes away. So we just end up being c1 is equal to 1. Taking this derivative and plugging 1 in for c1, we just get negative 2. Oh, just not squared, just 2. That goes here. Looks like that's what we get. And, oh, that's right. This is product rule. All right, so let's see. That's what we got here. So that's derivative. So plus just that. Okay. And now we get, again, 0. And this whole thing equals 3, though. So plug in 0. That goes away. Plug in 0. Get negative 2. And we get that. So adding this over, we find out that C2 is equal to 5. So now we have our solution. So C1 is 1. This is 5. And this is our answer. Now, we're not done yet because it asks us to verify that y2 is a solution. And remembering y2 was the equation t e to the negative 2t. So we want to verify is that's also a solution, just to check, right? Just for practice sake, so you can understand how it's going to go. All right, so we need two derivatives. All right, so just like we did for the first part, this is going to be a product rule twice. So derivative, this one is going to be 1. And then this derivative is just going to be 2, negative 2. And now again, take this derivative. So this is just itself. So negative 2. And on this side, again, it's just another product rule. So just give me negative 2. And then this becomes plus. And now we just plug it back into here. So it's all of this. I guess I could put those together. plus 4 times all of this. This gives me negative 8t here, plus 4 times the original. Okay, so let's see what happens. What's going on here? So it looks like these all cancel. Those go all to 0. This gives you negative 4 plus 4. It also gives you 0. So yeah, it is verified. Not too shabby. All right, one more. So the nice thing is, because it's always homogeneous, you can just follow the same process we've done before, right? Using the characteristic equation. So all this just goes up as 1 degree, so just be r to the third this time. And nothing really changes. So this time, just working your factoring skills. This is grouping method. So factor out an r squared. Factor out negative 1. So we get r squared minus 1 and r plus 3 equals 0. So we get r is equal to negative 3 and r is equal to plus or minus 1. So now we get 3 answers. So our general equation, c1 e to the, I'll just pick this one first, plus c2 e to the positive t, plus c3 e to the negative t. And there we go.